today's lecture I will continue to discuss the guided mode and their dispersion and polarization. Okay. So, before going into that details, I would like to discuss whatever we have derived the eigenmode full vectorial method, and stepwise I will be just giving you some outline, and then I will continue to discuss about guided mode solutions and their dispersion relations, and finally identifying the polarization of guided modes. Whenever you get a solution using full vectorial method, then you need to understand what type of polarization it is. There are some classifications I will be discussing on that. So I continue that as a reference I take help of silicon waveguide. This is a reef structure, parameters are W, capital H and small h, known as device layer thickness, and small h is the slab layer thickness and W is the waveguide width, and this slab layer h can be 0. When it is 0, that is called photonic wire waveguide. Photonic wire waveguide. So, sometimes strip waveguide and sometimes people call also photonic wire waveguide. So, for mode solution we need to know the refractive index, okay, of the core and also the cladding materials, and say operating wavelength, which wavelength you want to operate or you want to know the guiding property, that operating wavelength is needed, because this full vectorial method is a frequency domain, it is Fourier domain solutions. So, first step is that we call it as a step 0. Step 0 is mapping dielectric constant of refractive index profile, dielectric constant or refractive index profile. So, we have shown here the example of silicon waveguide, but it can be any waveguide, any cross section, any profile, refractive index profile, that can be represented as a n square x y, and in the x y plane you should have a map, every coordinate what is the refractive index. So, if it may not be possible to express using an analytical equation. For example, here if you see this refractive index for a certain coordinates only ND refractive index, and when you are considering y less than 0, entire box region refractive index is NS. So, it can happen that okay, it is a diffused channel waveguide, it can be some kind of doped waveguide, those type of waveguides you can represent with some analytical formula. If not, then you need a matrix form of the xy, you have every xy coordinates, you should have a particular dielectric constant or refractive index. So, that mapping, xy mapping of refractive index profile you need to go for a solution full vectorial method, using full vectorial method. So, now as we have already discussed that a dielectric constant profile for the waveguide, if it is given, that means the refractive index profile has a core and also surrounding it lower refractive index region will be there. So, if that is the case and that is 2 dimensional, then your waveguide mode, guided mode can be represented with a electric field and magnetic field. Electric field you will have a xy dependent some confined well defined mode solution, and then it should be travelling with omega t minus beta z. Similarly, magnetic field you will have a well defined vector field in the xy plane, and then it will be travelling with the same omega t minus beta z. So, that means this electric field and that magnetic field, they are coupled each other, and that is how it will be guiding along z direction, where this beta is defined by, so 2 pi by lambda n effective, W by C n effective. So, our first intention is that to find out this n effective index of a guided mode, and then next intention will be the electric field that is the xy dependent profile mode, that is a vector, that is a vector field, and that vector field can have x component, y component, z component. Likewise, magnetic field will have x component, y component, z component. So, we have all these 6 components are there and we need to solve for a given refractive index profile. So, this is for example, our vector wave equation we have derived earlier for electric field and magnetic field starting from Maxwell's equation. So, Maxwell's curl equation, we try to decouple electric field and magnetic field, considering that epsilon r is not a homogeneous medium, because it is a core cladding, everything will be there. So, you should have divergence d equal to 0, but you cannot write divergence E equal to 0, not equal to 0, because d involves epsilon 0, epsilon r, E. So, if epsilon r is xy dependent, then divergence E cannot be equal to 0. So, just using that thing, we have just written down the vector wave equations for electric field and magnetic field, that is what we have already derived earlier in the previous lectures. Now, step 1. What is the step 1? Step 1, from this vector equation, we can decompose into 3 scalar equation, one corresponding to x component and y component and z component. 3 scalar equation you can get, and here also you can get 3 scalar equation, and if you can solve those 3 scalar equations, second order differential equation, then you are done. Instead of solving all those 6 differential equation, we have shown that you can concentrate on 2 second order differential equation involving, from here you can find x component and you can find y component, x component equal to 0, y component equal to 0. These 2 equation, if you analyze clearly, you can see that you have Ex and you have Ey, and Ex also xy dependent and this also xy dependent, this is there. So, it is a second order derivative, partial derivative of this one, that is coming from del square. You know what is the value of del square? Del square is nothing but del 2 del x 2 plus del 2 del y 2 plus del 2 del z 2, and then you are getting like this, where you have clearly used this epsilon r, instead of epsilon r you have just written n square x y, okay, and you have considered this del z equal to minus j beta, you have considered, that means del 2 del z 2 equal to minus beta square, and minus beta square, instead of beta square you can write omega by c n effective. So, using that thing you are getting this equation, and because of the presence of delta epsilon r, we have this additional coupled term where Ex and Ey both terms are there, that is directly related to n x y. If this n x y is having some kind of inhomogeneous medium, that partial derivative of del x, this is ln, and that will be surviving, that thing you have to count. Okay. So, that is why we have just kept, as long as you are considering in general solution for any general waveguide. So, you can, this is the perfect equation. So, we can use these 2 second order differential equation, x component and y component. Then what we can get, for a given epsilon r x y and or n square x y, we can solve E x m, E y m and beta m. You can, these are, if you see, these equations are starting actually derived from Maxwell's equations, and Maxwell's equations we have used for linear. It is the Maxwell's equation in normal case, it is linear, right. So, you can linearize this thing, this equation and this equation, you can, it is a second order differential equation. You can actually represent them in a matrix form. In the matrix form, you can represent with something matrix of dielectric constant, and then you can write something E x, E y, and then you can have some value E x and E y and beta. So, this is a matrix E x, E y, and this is something beta, means n effective square term will be there, instead of an omega square by omega by c n effective, you can write beta. So, if you just represent this in a matrix form, this matrix can be created because of the epsilon r or n square x y. Okay. this thing in a difference form you can write down. I think there are various techniques how to solve this second order differential equation in a xy plane. So, you can represent like this, and if you solve this one you can find a eigenvector, a series of eigenvectors, okay, and corresponding beta. If you write their solutions are mth one, and then we will be writing beta m. So, for a set of eigenvector you get a eigenvalue beta m. So, after solving these two equation you are getting the eigenvectors with component exm, eym, beta m. M can run from just index. It is a basically indexing your eigenvalues. You can start from 0, 1, 2, 3, 4. So, if it is 100 of eigenvalues that you are solving, that depends on how much, what is the order of matrix you are forming using your dielectric mapping, dielectric constant mapping or refractive index mapping. So, that can be done numerically. I am not discussing this, that is out of the scope of this course. So, just how it is being it is calculated, that is what my intention is to explain that. All right. So, once you know exm and eym, you go for step 2. Okay. You have solved two second order differential equation to find out exm, ym for a different m can run from 0 to 1, so many eigenvectors, eigenvalues you are getting. For every given eigenvectors, say exm and eym, you can calculate actually Ez also, Ez x y m. How that is possible? You just start with a Gauss divergence theorem, divergence D equal to 0, and you know this divergence D means, as I mentioned earlier, that is actually epsilon r, E epsilon equal to 0, epsilon 0 can be outing here, epsilon 0 that is constant, you can take out, and this epsilon r, instead of epsilon r you can write n square x y. You know your refractive index epsilon r is n square x y, that is what you will be getting, and then E vector x y vector will be there. You know this is n square x y and E x, so divergence. So, you will have three terms, right. So, you will have say del x E x x y plus del y E y x y plus del z E y x y. Along with that you have to multiply n square x y. Every term you have n x square. That means you have to, this thing will be the first derivative and this thing will be the second derivative, second term, and this one will also be n square x y. And then again you do little bit simplification, del z, n square is not a function of z. So, this you are operating on a eigenvector E y, del z can give you minus j beta E y. Okay. So, using that thing actually you can actually find what is the value of E z. So, this is actually E z, right. Yeah. So, E z, this will be E z, yeah, that will be E z. So, del z E z, this is E y, this is E x. So, E z you can find z component, and if you start with mth eigenmode, then whatever you are getting you will be getting E z m. So, for a set of eigenvectors solved using first two differential equation and using beta m, you can find E z m. So, that means all the three components E x, E y, E z is solved now, that is in step 2. Now, for step 3 what we do, we take help of curl equation, curl of E equal to minus j omega, it is curl E, we know that expression, curl E equal to minus del b del t, right, del b del t, del t again minus j omega, and b can be written as mu 0 h. Okay. You can write, you have all the components for E x, E a y, E z you have solved already. So, use them here, then you can find x component left hand side, x component right hand side, y component left hand side, y component right hand side, z component left hand side, z component right hand side, you can equate, and then you can get the expression for h x, h y, h z. Obviously, wherever del z terms comes, you are using minus j beta. okay, by using this minus j beta. So, if you see, you can represent h x. If you know E z and E y, you can find h x. If you know E z and E x, you can find out h y. If you know y x, then you can find h z. So, all these three components for the magnetic field also known now. Just solving first order differential equation here, just you have to make a derivative of electric field components E z, E y, E x if it is known, then all the three components are known along with the beta m. So, that means for a given n square x y, I can get a series of solutions, eigenvectors, eigenvalues as a beta propagation constant, and then we can just inspect those solutions. Some of these solutions we will see that they are well confined within the core, they are guided mode and they have a corresponding eigenvalue, they will be travelling along z direction with a phase velocity this one omega y beta so on, that is travelling. But you can get also many more solutions which may not be giving you well confined solutions, and that may be it is like a leaky solutions. That is, in ray optics picture we have seen that sometimes when effective index solution or maybe angle coming less than critical angle. So, that means it will be leaking to the substrate or air, that is radiating mode. So, all the radiating mode solutions also will be you will be getting as a eigenvalue solutions, but you have to, after solving, you have to see the field distribution, electric field distribution and magnetic field distribution. If you see that you get a very well defined mode shape and outside at x y, if you are increasing outside the core and slowly decaying like a evanescent field, then that is a guided mode, otherwise they are leaky mode. That is the way normally we used to do, because you know normally when you are using certain technology and you have to rely on that technology and you are getting a structure which is convenient or which is comfortable by you are comfortable to fabricate using a standard technique. For example, CMOS fabrication technique, you have a certain process line where you can fabricate waveguide structure like this. H can be 0, all those type of things. So, that particular structure to solve you need really numerical method like full vectorial method. So, there are commercial software I have already explained, you can use them to solve this thing. You can develop by your own code also, computer program to solve, otherwise there are many commercial softwares are available, you can use that. Okay. So, now electromagnetic fields of guided mode, and that should be indexed by an integer number m, can be expressed like this: x component, y component, z component, and all of them will have a phase factor, it will be travelling with e to the power j omega t minus beta m z, and associated magnetic field also will have x component, y component, z component. All these component, when I am writing within this curly bracket, that means this one multiplied by this one, that is the x component, this one multiplied by this one, that is the y component, and this one multiplied by this one, z component. Similarly, for electric field also, that means all the field components, electric field, all the 6 components together will give you a certain mode. This is all solutions will give you a mode. That mode will have a phase velocity actually omega by beta m. Okay, that is actually travelling wave it is showing along z direction. That is what how we can represent. And not only that, once we know phase velocity, if we find some omega beta curve is not linear, omega beta relationship, then you at any particular frequency or beta value, you can get a slope of that curve d omega by d beta, then you can find that is actually group velocity. Normally, you know, group velocity is very important whenever you are sending any information modulating signal, frequency components are there as a data to transmit one place to another place. Okay. So, this is what we know, this mode solutions are obtained. Now onwards we will be thinking that we know how to solve the different field, different modes, and also beta m. These are now known, and we can solve any given structure, we will be able to solve. That can be numerically, that can be analytically if certain functions are favorable. Otherwise, we will be considering that okay, these modes can be calculated or evaluated very easily. Okay. That is for sure, we are taking granted now onwards. Now, what about the power carried by a mode? say mth mode. You know the power carried by mth mode, you can use your Poynting vector Poynting theorem, that means energy flow per unit area per unit time, and here we have to consider along z direction. Okay. So, along z direction EM electric field and magnetic field complex conjugate, and you have to take real part and then half, that will give you the average time average power flow, time average power flow. And if it is mth mode, we are writing mth mode. And if it is waveguide cross section, though waveguide core is well defined, but you know mode field, it can be extended outside the core as a evanescent tail. That is why we can say that entirely if you integrate even up to the infinity, if you integrate x equal to minus infinity to plus infinity, y equal to minus infinity to plus infinity, that is fine, because for a guided mode at infinity, if you are integrating from minus infinity to plus infinity, you will be getting only the field around the core region, core and surrounding region. So, in fact, if you just extend your integration minus infinity to plus infinity for convenience, that is fine. You can put down that limit, but you have to take along z direction, you have to take a z component and then you have to integrate the Poynting vector along z direction and then you have to integrate. So, that is why we are taking a dot z, that vector, whatever vector you are getting, that you have to take projection along the z axis, and that will be the energy flow along z direction. And if you have all these 6 components you use, right, then this is Ax, Ay, and you have to write E cross H, right, E cross H and z component. Z component E cross H, if you just try to find out, that means this is something like this matrix form you can write, right. So, then you can write Ex multiplied by Hy, Ex multiplied by Hy star, of course, you are taking A cross B, right, E cross H, and then minus Ey Hx, that is actually z component, this is actually the z component, if you just take E cross H, considering all the 6 component presents in a mode. So, that mode will carry energy along z direction if you solve this equation. If you can integrate this equation, if you know the x y dependent profile for the electric field of the x component and magnetic field of y component and vice versa. So, that means only x and y component of the electric field and magnetic field, that actually contributes energy flow along z direction. Okay. So, next thing, what should we do? Okay, let us try to find the dispersion relation. We know that how much power it will be flowing, energy it can carry by a guided mode, we can calculate, right, once we know the mode field distribution and propagation constant. Now, we know that energy flowing is not enough, this type of waveguide or optical interconnect, fiber optics communication, etc., we want to transmit data. So, data transmission means you have to follow the group velocity and dispersion relations, all those are very important. So, we need to study now dispersal relation for the individual guided modes. You consider a certain waveguide dimension, for example, here standard thickness, device layer thickness is h equal to 220 nanometer. We have consider assume waveguide width is 1 micrometer and slab height is 0 if we consider, and standard ND equal to 3.4778, NS equal to, that means substrate box refractive index 1.4657, and cladding refractive index we also consider that is the air cladding, that means 1. It can be oxide also, as I mentioned again and again, and we know that the waveguide solutions comes, that means every mode eigen mode solutions comes with n effective m, a series of effective indices and corresponding beta m you will be getting, right, and we represent the mode, mth mode, associated electric field is expressed like this is a vector and this is also a vector, right, x y dependencies we have written. Now, if we solve, if we just plot, we just remember that this refractive index, when I am saying this is actually for lambda equal to 1550 nanometer, and that is a bulk material, bulk silicon refractive index is this one at lambda 1550, and bulk silicon dioxide, this is the refractive index at 1550 nanometer. Here is the all the wavelength is normally 1 refractive index, but when I try to solve the dispersion relation, we have to sweep the lambda value. Okay. We want to see the beta versus omega. So, beta equal to omega by c n effective omega, that is the things. I want to calculate effective index as a function of omega or lambda, omega equal to 2 pi c by lambda. Okay. So, I have to sweep the lambda. So, if you sweep the lambda to see what all the solutions, what you have to do, we need to know lambda dependent refractive index of the material dispersion we need to know. But here in this case we have considered that the material dispersion is almost 0. There are material dispersion. For the discussion purpose, for present discussion, we have considered this material dispersion is 0. That means as a function of, because you consider 1500 nanometer to 1600 nanometer, very short range if you consider. Okay. Within this range, if you are considering, within that range you can say that this refractive index is change may be very minimum. But whatever that thing is there, you must consider, of course. But what I want to discuss here, that when a electromagnetic wave is propagating as a guided mode confined within a certain area within 1 micrometer, vertically 220 nanometer, you know, 220 nanometer vertical depth, and you are considering lambda equal to 1500 nanometer. So, it is much lower than the wavelength. The thickness of the waveguide dimension is lower than the wavelength, width is in the order of wavelength. Okay. So, in that range, if your wavelength is varying a bit, then your mode solutions will vary rapidly. Okay. That is qualitatively you can understand. So, whenever you are talking about a waveguide like a silicon waveguide, which is very small cross section, 220 nanometer, width may be also 400, 500 nanometer, here we are considering 1 micrometer. So, in that case your operating wavelength is 1550 nanometer. So, more than the dimension, and because silicon has a very high refractive index, that is why the wavelength, you can pack your electromagnetic wave as a mode within an area which is much lower than the wavelength of the electromagnetic wave in the free space. Okay. So, that is the reason, but at the same time you should keep in mind that if you change the lambda slightly 1500 from 1500 to certain other wavelength, then you will see that your mode will see different type of mode field distributions as well as different type of effective index solution. And we tried to solve with this parameter, and we found that we actually tuned the wavelength in our solution from 1.3 micrometer to 2 micrometer. That means 1.3 micrometer we have considered, because you know lambda equal to 1310 nanometer, that is the second generation communication window, fiber optic communication window, and that is also transparent in silicon. And we have just for understanding purpose we calculated also 1.55 as well as extended up to 2 micrometer, just for understanding purpose. Okay. And in the x axis, if you see, this is the wavelength 1550 nanometer, it is marked here. Okay. And y axis we are considering effective index, and if we see, if we concentrate on mode 1, that means beta 0 we are considering equal to omega c by n effective 0, and you can consider beta 0 equal to omega by c n effective 0 omega, or you can consider 2 pi by lambda n effective 0 lambda. So, if you lambda vary, okay, if you vary the lambda, then you calculate n effective. Okay. Then that n effective versus lambda curve we are plotting here. Effective versus, you are tuning the lambda value and you are calculating the effective. You are tuning the lambda, you are solving your full vectorial equations, all the equations you are solving, and you are getting, and since you are getting eigen mode m equal to 0, all the eigen values corresponding to m equal to 0, 1, 2, 3, 4, you just plot it. So, this is actually fundamental mode 1, this is mode 2, mode 3, mode 4, mode 5. So, m equal to 4 means mode 5, because we are counting 0. So, the take home message here is, as you increase the wavelength, if you are just restricting yourself with a one mode, you see effective index is reducing almost like a linear, but it is exactly not linear if you just amplify and check. And next mode, if you see effective index reduced, but same trend almost, but it is at longer wavelength, it is actually the separation is more. And next mode, if you see an effective, if you calculate, and see effective index as a function of lambda, it is coming like that, and this way and this way, and then it is like this. And here this dashed line, if you see, this is marked at NS. NS means substrate refractive index, that means silicon dioxide refractive index. You are getting a solution sometimes. For example, if you just cross above 1550 nanometer, your solutions you are getting effective index, it is lower than the box, the lower cladding refractive index. That means that is obviously not a guided mode for sure. Looking into this, you can just conclude that. So, beyond this one, m equal to 4 will not be guiding. So, that means beyond 1550 nanometer wavelength, you may have only this one solution, and second solution, third solution, fourth solution, 4 guided modes will be there, and corresponding effective indices you will be getting also. Okay. So, if you just consider, if you are designing one wavelength, okay, one particular waveguide parameters 221 micrometer everything, and suppose you are operating at 1310 nanometer here 1.3 micrometer, then definitely you are getting 1, 2, 3, 4, 5 different guided modes, multi-mode waveguides. Okay. However, if you just operate same waveguide dimension, if you go further, say maybe 3 micron, 4 micron, of course, beyond 4 micron you cannot use that, because beyond 4 micron it will be absorbed by the lower cladding. So, if you see that this trend will come like this will be coming like this. So, after certain value you will see here maybe 3.3 micrometer, right. So, here you will see it will become single mode. So, if you consider these waveguide parameters and if you operate beyond 3 micrometer for example, then it can be single mode waveguide. But as you reduce your wavelength, more number of modes will be coming, these modes will be coming. Okay. So, it will become more and more multimode. So, choosing the correct parameters, waveguide parameters is very important to have to restrict, to control the number of maximum guided modes in the waveguide. Fine. Okay. Now, next thing is that this is actually we can call as a one way of calling it as a dispersion relation, effective index as a function of lambda. Same thing, because we are interested to know omega beta curve, omega versus beta, omega beta relationship, because from there we can directly extract what is the phase velocity at a particular frequency and what is the group velocity at a carrier frequency omega c, for example. So, what we could do, we can actually this wavelength we can convert into lambda equal 2 pi c by lambda equal to omega. So, lambda can be converted into omega, and that omega we put in the x axis, and effective index whatever we are getting, we will be multiplying that with omega by c, n effective. If we multiply, then it will be beta. So, if I just multiply omega by c, corresponding omega by c, and n effective we multiply, then you will be getting beta. So, if I just plot, same thing we are plotting in omega beta, it is just a little bit scaled omega beta directly, then you can get this mode 1, how it will be looking like, mode m equal to 0, m equal to 1, m equal to 2. The nature will be, you see, for example, here m equal to 3 and m equal to 2, they are crossing at this particular point, because you know sometimes you can have a degenerate solution also. Say for example, at this frequency you get a for m equal to 2 and m equal to 3, you are getting a same beta value, that means same in effective index. So, that type of solutions also can have. What is the reason for that? That is because you are getting different eigen modes, some of the eigen modes can be can have eigen values same. So, how that is possible, one particular mode and another mode they are same, because that actually depends on how the electric field and magnetic field distributed around the cladding. Depending on that, actually that particular mode, how it will be traveling with a certain phase velocity, that decided. Suppose some field you will see in the vertical direction it is extended more for a certain field component, another field maybe in the horizontal direction it is extended more, such that total impedance or total effective index you are seeing in both cases, they can be identical also. So, this type of identical solution does not mean they are same mode, but they are different mode, field distribution can be different, but eigen value can be same. Eigen vector can be different, but eigenvalue can be same. This type of things we can call as a degenerate solutions. Okay. So, next we move on to look into the different components. For example, we take another waveguide parameters, silicon waveguide parameters, W equal to 500 nanometer, H equal to 220 nanometer, small h equal to 0. So, that means a completely photonic waveguide and 500 nanometer submicron. And of course, you should remember that all the solutions you can solve by using any mode solver, eigenmode solver, commercially available, or you can develop yourself. The method I have shown how to develop. So, now if you consider these waveguide dimension and then you use your mode solver and find different solutions. When you get the first eigenvalue m equal to 0, that means first eigenvector, that means Ex, Ey, Ez component you will be getting and corresponding beta value you will be getting. That beta value corresponding N effective you are getting like this 2.3828, which is higher than the slab effective index. That means NS is how much? NS not given here, NS is 1.46 something like that. So, N effective 0 is more than that one you are getting, right. So, once you get that is guided, that means that is a confined mode, then we look at individual field components. First we looked at Ex component, X component of the electric field, Y component of the electric field, Z component of the electric field, all of them are present. And if you see the scale, this color bar here shown, you see the red is the maximum, that means at the center it is normalized to 1, and then as you go, this is your waveguide core, it is shown here rectangular box, and at the center the Ex component is maximum there, and then as you go away it will be reducing. But at the boundary you see boundary there is a discontinuity is there, because you have to see the continuity equation. So, normally Ex is the normal component in the vertical boundary here. So, normal component it is continuous only, D displacement vector is continuous, dielectric constant different in both sides, that is why electric field will see some kind of so called discontinuity, but electric field you can see here. In that scale if you see Y component if you see is very weak, you see this somewhere here 0.2, 0.18 or something like that, but only visible in the corners. Most of the places it is actually almost 0. That means Ui component almost it is almost nothing with respect to Ex, but there some field component is there, and Z component it is a relatively stronger. So, you have Ex component, Ez component, but Ui component is not there, almost 0, but you cannot say, rule out completely, some value is there. Now, for the same mode I have all the 3 components, how it will be looking we have seen. Now, what is magnetic field for the same mode? If you see Hx component here you can see some value here, but you see scale 10 to the power minus 3, that means Hx component is there, but very weak. But what about Hy component? You see Hy component is also there 10 to the power minus 3, some component is there, and Az component is also 10 to the power minus 3 is there. Okay. So, overall I think here this scale must be a little more, it will be, I think here somewhere some mistake is there, Hy component should be higher. Okay. Now, of course, it is magnetic field strength you have to relate with the electric field strength, that is why it is showing, but this Hy component is the dominating factor here, it is scaled with the Ex value, that is why it is lower. Here also it is lower, but in the corner, and Hz component is also similar things. Now, go to the m equal to 1 solution. Next eigenvalue, eigenvector, you see Ex1 is almost nothing, it is a 0.7, this scale is given, and Uy1 that will be stronger, it is up to 0.9, you are saying that this thing field distribution is different now. Okay. It is a higher order mode, field distribution is different, and then you see this one Z component is like this. Okay. So, all the 6 components are present, some of them are stronger, some of them are not stronger. Okay. So, we know how it will be looking like all different field distribution, for particularly silicon waveguide we are confirmed that whatever we predicted in full vectorial solutions, that all the 6 components will be there, they are coming. Okay. Now, see this, this is for magnetic field. Okay. Now, we based on the fraction of the components, normally people used to categorize, classify polarization of the guided mode. So, that is why now we want to discuss polarization and field distribution of the guided modes. So, polarization, what different type of polarization set we can have. So, sometimes some solutions you may get, say in this configuration, this is x axis, this is y axis, x component will be there, z component will be there in the of the electric field. So, that means electric field is in the xz plane. Xz plane means it is parallel to the tangential to the substrate. So, electric field will be oscillating only in the plane of the substrate, plane of the waveguide surface, and magnetic field will be in the yz plane. X component is not there. So, magnetic field will be in the vertical plane, yz plane. So, if electric field is oscillating in the xz plane, z is the propagation direction, and magnetic field is in the yz plane, it has a y component and z component, electric field x component and z component. Then this type of mode we will call as a T-like mode. So, in 1D waveguide we know that it is x component will be there electric field and y component will be there in the magnetic field, that is actually so called T polarization. But in this case you have electric field in the plane, because 2D confinement. So, you cannot just say that only one direction. So, it will be in the one plane and magnetic field in the vertical plane, that will be called T-like. This is just a nomenclature, just for understanding purpose. It is all whatever you are getting as a solutions, that is that absolutely you have to consider, but sometimes some solutions you will be getting in this nature. If in this nature we will be calling that T-like mode, because this T-like mode we can easily refer for certain application. If it is T, this type, it is sensitive to this type of application. If it is some other orientation, then it will be sensitive to other type of solutions. So, likewise we can have another option, that your electric field can be in the yz plane, vertical plane, and magnetic field in the horizontal plane. So, T-like mode, electric field in the horizontal plane, magnetic field vertical plane, and now magnetic field in the horizontal plane and electric field in the vertical plane. So, that type of field will be called mode will be called TM mode. So, transverse magnetic, transverse electric. Transverse electric means your, that means it is a transverse means in the plane of the waveguide electric field, and transverse magnetic field in the plane of the waveguide. So, that will be TM mode. And if all the components are there, for example like this, all the components, then we call that as a hybrid mode. So, in this case your EY component is not there, in this case EX component is not there. And if both EX and EY component, EZ component has to be there some way, and if EX and EY components are comparable, then we can call that as a, we cannot classify like T-like or TM-like mode. Electric field and magnetic field is no more in a plane. It has all the three components, X component, Y component, Z component. It is not either XZ plane or YZ plane. So, it is actually called hybrid mode. So, this is three different types of classification normally in the textbook and literature people refer normally. So, some solutions you get like T-like mode, we can say that okay, it is T-like mode. Some solution will be, these components will be there, there is TM-like solution. So, that depends on all the parameter of course, W, capital H and small h, this waveguide parameter, ND, NS, NC, all those parameters involves. Okay. Now, we tried to see these three different type of solutions for a certain waveguide here, W, H, small h. We consider H equal to 220 nanometer, which is very popular in CMOS foundry, and we consider lambda equal to 1550 nanometer wavelength operation. And because this is a device layer we are getting from this wafer as we are buying. Now, we would like to, in our hand, if I want to fabricate a waveguide or design a waveguide in our hand, then we have two parameters. I can control W or this small h. In this plot, what I tried to show here, that waveguide width varied from 300 nanometer to 700 nanometer, and the slab height, that is actually varied from 0 to h can be 0 to 200 nanometer. Total height is 220 nanometer, that is given fixed, lambda 1550 fixed. Then for every waveguide width I varied your small h and then tried to see the solutions every point. Similarly, I change my W value here and I vary again small h, then try to map a plane. I tried to find the guided mode solution in WH plane, WH plane. Suppose if I consider this point means I have to consider, okay, W value is here and H value is here, and in this if I use this H value and this W value, then what type of solutions I will be getting? I will be getting only one solution, and that is T like mode. Okay. If I similarly, if I just consider this point, that means corresponding W value this one, if I solve this one, I can get H this one, there also I will be getting T mode, single solution. So, this region, if you see this region, if you see this region, for any W and H value you get, it will be like a T like mode. And now I say that T like mode, that means Ex component, Ez component will be there and Ui component will be 0. Normally Ui component hardly you will be getting 0, because earlier we have seen that component also has some value, but when I say 0, it is negligibly small, but it will be a certain value, maybe 5%, 10%, that is also still we can call as a T like mode. So, this T like mode we can quantify the T like mode or TM like mode, then hybrid. How to quantify that? For that purpose, normally in literature people use two different figure of merit. Okay. What is called T mode polarization fraction. If you say T mode, normally we say that X component will be dominating, X component and intensity square we are taking, integrating over entire, only X component square I am integrating over the entire waveguide, and then I am normalizing with the X component or Y component total intensity. Intensity contributed by X component, intensity contributed by the Y component, I am adding them and normalizing to the what is the fraction of Ex component, that is means what is the fraction of Ex component, this measures. So, if this fraction is very high, close to 90, more than 90%, then we will call it is a T polarized. If it is less than 50%, maybe only 10% or something like that, that means this fraction will be higher. TM polarization mode polarization fraction will be higher. So, we will be calling that as a TM mode. So, based on that, when we find something T polarization fraction more than 90%, then we will be calling T, and if it is less than 90% or if it is something 10%, this is more than 90%, then it will be called TM, otherwise we will be calling as a hybrid. So, in that sense, we find different zone in WH plane, where you will be getting single mode, where you will be getting multi mode, and where you will be getting hybrid mode, and this region you will be getting single mode T, and this region, this particular region under the blue curve, you will be getting both T and TM mode, one single mode T, another that is not really a single mode waveguide, two modes are there, but one will be exactly T like mode, another will be TM like mode. So, two modes will be there. So, that way you can easily follow. For a silicon waveguide, we have calculated this thing to find out, suppose I need a certain type of mode to be guided, and this should be single mode or this should be multi mode, I need both T and TM, then I can, looking into this map, I can find out, okay, I need this much W value and this much small h value. Okay, fine. So, now this is something we have calculated also, that when I just consider W equal to 400 nanometer, H equal to 10 nanometer, you try to find out the solution for M equal to 0. M equal to 0, you will be getting T like mode, because T like mode polarization fraction you will be getting 96%. That means you are getting Ex M x0 xy square divided by, this is integration dx dy, and Ex square dx dy plus this one you will be getting 96%. That means Ex component is 96% compared to the total value of Ex and Y. That is why we were considering this is a T like mode. Okay. And if you are solving for the higher order mode, okay, fundamental mode, that is actually M equal to 1 you will be getting. Then you are getting TM like mode, that means EY component is 91%, EY component fraction. That means electric field will be dominating in the y direction, and in this case electric field will be dominating in the x direction. So, this one I will be calling like a TM like mode, and this will be calling as a T like mode. So, here that is why it is 400 nanometer. If you are just considering 400 nanometer and H equal 10 nanometer, some point you are considering here 10 nanometer here. So, you see one it will be still, some people used to call it as a single mode, because one is completely T like mode, another is completely TM like mode. So, that is why it is single mode, but both the polarization can guide that way. But in principle, in mode solver point of view, it is actually still multi-mode, 2 modes it supports. Okay. Similarly, for 700 nanometer we have a fundamental mode and 700 nanometer and slab height 50 nanometer. So, 700 nanometer, slab height somewhere 50 nanometer here. So, it is a multi-mode region. So, fundamental mode you will be getting T like mode, where T like 99% polarization, and next higher order mode also will be T like, no TM like, both the mode, m equal to 0 also T like, m equal to 1 also T like, and in this case m equal to 0 is T like, m equal to 1 next eigenvalue solution like a TM like mode. So, that means this T like TM like mode, it is our own definition, but ultimately full vectorial solution, this vector wave equation whatever you are solving, that is the ultimate things. So, with this I just stop this lecture today, and I will continue next about the orthogonality condition in the next lecture. Thank you very much.